Okay, so in this lesson, we're going to go over probably the most important topic in all statistics, because we're going to be using this throughout the remainder of the course, and that is what is known as a normal distribution. So our goal by the end of this lesson is to be able to use this normal distribution to be able to calculate areas in what's called a normal curve, and be able to use it to also, solve real life application problems. And we're going to learn about how we can determine if a set of data is normal using graphical and numerical evidence. Okay, so first let's go over the basics of what density curves are. So density curves have to have two things. They have to be above the horizontal axis, or they're going to be on it. So the area is always, like positive, you could say. And the area has to add up to exactly 1. So you can think of this as like as 100%, but in terms of like the context of a problem, the area has to be able to be multiplied or added to total so that it will equal one unit. So here are some examples. Now, the common one we're going to see and use a lot is are going to be bell shaped, but they don't have to be like that. They could be double peaked, maybe something like this, or they could be uniform, where it's basically you could have self-symmetry all throughout, or it could be skewed to one side or the other. Now, like we learned in previous chapter, distribution basically describes the overall pattern of a set of data, and density curves basically describes the overall pattern and distribution. So it's eventually going to be used to calculate probabilities, which you use to, answer real life problems. And we look at this probability, or look at these probabilities as the proportion of area underneath these curves. So we like to focus on two main measures of center when we're dealing with density curves. These are the median and mean. The median of a density curve is going to be where it divides the area in half. So 50% to the right, 50% to the left. The mean would be where it would bounce if we could hypothetically make a density curve, out of solid material, if it was like a real life, structure. So like, here are some examples. If you had like density curves that were symmetric, then you'll be balanced right in the middle. It's kind of, obvious. But if it was skewed to the right, the balance point would be a little further to the tail end of the distribution. Now, there are a couple key things you have to know about the relationship of the mean and median when we're dealing with density curves. First is that in a symmetric curve, which is the ideal situation, the mean and median are going to be equal. Now, if you have the curve skewed, let's say to the right, then the mean is going to be further to the right or towards the tail side than the median. So the mean is going to be greater than the median. Now, if it was skewed to the left, it would be the opposite. The mean would be less than the median, or it would be less in the value. Now, these are important because we're going to focus on a specific type of density curve known as normal curves, which describe what are known as normal distributions. Now, they have basically these general properties that we're always going to be, dealing with, and they need to be symmetric. They're always going to be single peaked, and they're going to be bell shaped. And we mathematically define them and describe them by determining what the mean value is. So like we will list the numerical value of the mean, and then also the numerical value of the standard deviation. So remember, we like to use the Greek letter mu to represent the mean in statistics, and we like to use the Greek letter sigma to represent the standard deviation in statistics. Now, like we just showed, the mean and median in a symmetric curve are going to be in the middle. They're going to be the same. Now, in the cases where we have normal distributions that are, going to be more steep in the middle or more flattened out, we're going to be looking at the value of the standard deviation. So the standard deviation is actually what controls how spread out the curve will be. the larger standard deviation, the more spread out it's going to be. So it's going to be like more flat, like more like kind of like a like a pancake shape, you could say. The smaller it is, the more steep it's going to be. So it's going to have more area, you know, closer to the middle. And mathematically, the way we can determine this is by calculating what are known as inflection points. So the standard deviation is essentially the distance from the center to what's called an inflection point or a change of curvature point. So think of it as if you're going to be, you know, going uphill to downhill. So like in this curve, we would be, you know, in this up to here, we're kind of trending upwards. But after this point, we tend to be, you know, kind of sloped down. So you're sloping down up to here. Then after here, we're again going upwards. Kind of we have what's called a concave up portion here and a concave down here. So the inflection points or the standard deviation values will be located at approximately these parts of the graph. For this one, you know, again, we're looking concave up, which would be up to here. Then after this point, we're going downwards. We have like a concave down portion. So the, you know, inflection points would be, you know, somewhere like these points. And if you take calculus, you'll, you know, you learn about this or we'll learn about this. But it's actually not too important to know the mathematics behind this. The normal curve actually follows this equation, f of x is equal to 1 over the entire square root of 2 pi times the standard deviation, all multiplied by e to the, this entire expression, e to the negative x minus mu squared over 2 mu squared. If you're actually interested in learning about this, I'll make another video. But this is something you're not going to have to worry about being tested on in regular statistics. All right, now let's get into the key point of this section, the normal distribution. So the normal distribution, we describe it by writing n of mu comma sigma. That means that this normal distribution has a mean with value mu and a standard deviation with value sigma. It's kind of like how when you first learn how to represent functions, we're going to be representing all different types or all different, you know, values of normal distributions in this notation. So at first it's going to seem a little weird, but as we go through the course, you're not even going to think about it. Now, normal distributions are a big deal in statistics because they actually really help describe real distributions of data. So these could be like scores on tests, like if you were to take the SAT or if you're taking an IQ test or many standardized tests throughout your life, those sets of data are actually going to follow a normal distribution. If you were to actually make a lot of repeated measurements of something like, you know, the length of, you know, or the length of the diameter of a tennis ball or a basketball over and over, you're going to see these values follow a normal distribution. Normal distributions describe actually a lot of data in biology, like the weights of babies, the heights of people, you know, females, males, you know, elderly, you know, all sorts. So you're going to be dealing with them a lot if you go into, like, you know, a psychology major or you know, even in many science majors. So comparatively, you get very familiar with this basic rule, and it's known as the 68-95-997 rule. And it's essentially because the normal distribution will always follow this pattern of percentages in terms of their standard deviations. So what this 68 means is that 68% of the data values will fall within 1 standard deviation of the mean. So 68% of observations, we say, will be within 1 standard deviation or 1 sigma of the mean mu. Okay, so let's draw what this means on this normal curve. So here, these tick marks represent standard deviation values. So this would be, the mean, or right at the center, because there's, it's not going to be any distance away from the center. So we're going to divide, we'll draw a line represent the middle of this curve. There's your mean. Now, this and this represent 1 standard deviation to the left and 1 standard deviation to the right of the mean. And so this first part of the definition, the 68 part of the rule, means that 68% of the total area is going to be between here and here. So let me draw this a little higher out so we can show this a little more clearly. So 68% of the entire data is going to be from here to here. That's going to be in all normal distributions. And then that means that since this is a symmetric curve, 34% of the data will be in here and the other 34 will be in here. Now, the second part of the rule, the 95 part, means that 95% of the observations will be within 2 standard deviations of the mean. Oh, let me write that a little further. So on this side, that's 2 standard deviations to the left. Over here, this is 2 standard deviations to the right. And 95% of the total area will be from here to here. So let me extend this line a little further up so we can show this a little more clearly. So 95% will be from this line to this line. All right, so now breaking this down, since this is again a symmetric curve, half of 95% will be from here to here, from 0 to 2 standard deviations, and the other half, 95%, will be from 0 to -2 standard deviations. So half of 95% is 47.5%. So 47.5% lie from the center to there, and then the other 47.5% lie from here to here. Now, that being said, since 47.5% lie in these 2 regions, that means 13.5% lie here, because 13.5 plus 34 makes 47.5, and another 13.5% lies over here. And you probably are picking up on this now. The third part of the rule, the 99.7 part, means that 99.7% of the observations lie within 3 standard deviations of the data, or within 3 standard deviations of the mean. So from here to here, -3. I'm going to do this from the bottom. So 99.7% of all the area lie from here to here. Now, again, using, the principle that this normal curve is symmetric, from the mean here to here will be half of 99.7% of the total area. And so that means that you divide 99.7 into 2 and you would get 49.85%. So from here to here on this side. And the other 49.85% would be from here to here on this side. And then this small portion would be what you would have to add to 34 and 13.5 to get to 49.85, or what you add to 47.5 to get to 49.85, which is just going to be 2.35. So 2.35% of the total area lies in this small area, and 2.35% of the total area lies in this small portion of the curve. So almost the entire area lies in 3 standard deviations of the mean, but let's not forget there's still a little bit left over. So since the total area has to be 100%, that means there's 0.3% left over in here and here. So if you just take 0.3% or 0.3 as an area and divide it into 2, that means you're going to have 0.15 of the total area from here to here. Or you can just think of that as 0.15%. So 0.15% here and 0.15% there. Okay, so let's do a practice problem, because again, that always makes this stuff make a lot more sense. So let me switch over here. Okay, so in this example, it says that the batting averages of Major League Baseball players has a mean, or had a mean of 0.261 and standard deviation of 0.034 for these 432 for people at bat, you could say. The distribution is exactly normal with a mean of 0.261 and a standard deviation of 0.034. So part A, we're going to sketch an normal density curve for this distribution, and we're going to label the points that are 1, 2, and 3 standard deviations from the mean. Okay, so part A, we're going to just draw a sketch, and you're going to have to really practice your bell curve drawings, because you're going to be doing this a lot. So again, I always like to start at the middle, or the mean, then just sketch about 3 equally spaced lines to one side as best as you can. 1, 2, 3, say. And remember, these are standard deviations. So that's again 0. Think this is 1 standard deviation to the right. This is 2 standard deviations to the right, 3 standard deviations to the right. This is -1 standard deviations. So 1 standard deviation to the left, 1 standard deviation to the right, or 2 standard deviations to the left, and then 3 standard deviations to the left. So remember, the mean always goes in the middle. So this is the mean value. So the mean here would be 0.261. And standard deviation is 0.034. So if we're going to figure out what the value is 1 standard deviation away, all you do is add 0.261 to 1 times 0.034. I'll give us 0.295. If you want to figure out what the value is 2 standard deviations away and to the right of the mean, you just add 0.034 twice to the mean of 0.261. So we can just go ahead and add it again, 0.034. and we get 0.329. And then to figure out what the value is 3 standard deviations to the right, we just add again that 0.034 to the mean, 0.034. 0.261 plus 3 times 0.034. Get 0.363. Okay, now it's very similar for the values on the left, except you just add or you just subtract that many standard deviation values away from the mean. So for -1 standard deviations or 1 standard deviation to the left, you do 0.261 minus 0.034, and you get 0.227. For 2 standard deviations to the left, you just subtract it again. You just subtract 0.034 again from the mean of 0.261, you get 0.193. And for 3 standard deviations away, you just subtract 0.034 again, and you get 0.159. Okay, so that's the first part. Now, what percent of the batting averages are greater than 0.329? So if we're talking about the percent that's greater, we want to find essentially the area to the right of 0.329 or the area to the right of 2 standard deviations. So again, since this is a normal density curve, that means it follows this pattern. And so to find the area to the right of 2 standard deviations, we just add up these 2 percentages, 2.35% to 0.15%, and that will give us the total area to the right. And you would just get 2.5, and remember as a percent, so you could say 0.025 is in the area, or 2.5%. Just make sure you write it like that. So 0.0235 plus 0.0015. So 2.5. So we say 2.5% of the batting averages are greater than 0.329. Now part C, what percent of the batting averages are between 0.193 and 0.295? Well, we're essentially just trying to find the area from this value to this value. We want to find this area, the area between -2 standard deviations and +1 standard deviation. And again, since this is going to follow the normal distribution shown here, we're just trying to find the area from -2 to 1. So we just add these 3 values up. We have 13.5, 34, and a 34. So this would just be, and then let me just go straight and write it as percent. 13.5% plus 34% plus 34%. And we're going to end up with 81.5%. So 81.5% of the batting averages are between 0.193 and 0.295.